We now continue on with our discussion about ionic compounds. Previously, we have talked about the formation of ions from a single atom. So for example, calcium loses 2 electrons and forms Ca2 plus, or the calcium cation. However, we could also have a group of atoms, that collectively forms a charged entity or ion. And when we have this group of atoms that forms an ion, this is called a polyatomic ion. So a polyatomic ion. So a monatomic ion is an ion formed from a single atom through the loss or gain of electrons. A polyatomic ion is an ion formed from a group of atoms through the loss or gain of electrons. For example, if we have oxygen and hydrogen and collectively they gain an electron, this is OH minus. This is called the hydroxide polyatomic ion. Another common one is sulfate. So sulfur and 4 oxygen atoms, and collectively they gain 2 additional electrons to have a -2 charge. And then this is oxalate, so we have 2 carbon atoms and 4 oxygen atoms, and this unit has a -2 charge overall. So these are examples of polyatomic ions. But there are many different types of polyatomic ions, and so here's a shorter list. So when I was in undergrad and college, I had to learn a whole list of them. I won't be as mean to you, so there's only certain ones that I hope that you know by the end of this course. And we'll discuss which ones, but here's one list with many types of polyatomic ions, and then here's an even more expanded list. But if you're ever solving problems, it may be involving these polyatomic ions, it may be good to have this with you. But there's a little trick for remembering some of the more common ones. So what I use is Nick the Camel, so a mnemonic or memory aid. Nick the Camel ate clams for supper in Phoenix. So Nick the Camel ate clams for supper in Phoenix. And so we look at these words: Nick, camel, clams, supper, Phoenix. And the number of consonants is equal to the number of oxygen atoms. So the number of consonants is equal to the number of oxygen atoms. And the first letter or letters of the word helps us to know which element. So for example, Nick, N, and the number of consonants in this word, so that is letters that are not A, E, I, O, U. So these are vowels. So any other letters are consonants. So N, C, K, so those are consonants. So that tells us how many oxygen atoms. So NO3. And then the number of vowels tells us the charge. So there's 1 consonant, I, so NO3 minus. So this is nitrate. Then carbon, and then how many consonants? So 1, 2, 3, so CO3, 2 minus, so that's carbonate. Then for this one we use both, so Cl and then O, so this is chlorine, so Cl O4 minus, and this is called their perchlorate ion. Next, so you try to do the last two. Okay, so pause it, come back. So SO4, 2 minus, that's sulfate, and PO4 3 minus is phosphate. But if this method doesn't work, then the old-fashioned way of memorization still works in most cases. So nitrate, carbonate, perchlorate, sulfate, phosphate. And like I said, it was the more extensive list. So we'll look at some patterns overall in the polyatomic ions. So most of the polyatomic ions have a negative charge. So that means they have gained electrons. So most of the or they have additional electrons. Most of the polyatomic ions have a negative charge, which can vary from -1 to -3. Only two positive ions are commonly encountered, NH4 plus, which is ammonium, and hydronium, H3O plus. A few of the negatively charged polyatomic ions, such as hydroxide and cyanide, have the ending "ide", so "ide", so hydroxide, cyanide, peroxide. And then a number of 8-ite pairs exist, pairs of ions exist. And so essentially these are very similar pairs, except they differ in the number of oxygen atoms. So the 8 ion always contains one more oxygen atom than the ite. But both the 8 and the ite ions of a pair carry the same charge. So if we know nitrate, then we also know nitrite, because nitrate has one more oxygen. So this is nitrate, NO3 minus, and this is nitrite, NO2 minus. If we know sulfate, then we know sulfite. So SO4 2 minus is sulfate, and SO3 2 minus is sulfite. And then here is kind of a group of similar polyatomic ions. So starting with perchlorate, so ClO4 minus. Then we have one less oxygen, so this is called chlorate. Then we have chlorite, so notice again chlorate and chlorite. And then we have ClO minus, which is hypochlorite. So Superman, so perchlorate, and then chlorate, chloride, hypochlorite. And these with oxygen atoms are called oxyanions. So these polyatomic ions with oxygen atoms are called oxyanions. And so while the oxyanions differ in terms of how many oxygen atoms are present, there are some pairs that differ based on differences in the number of hydrogen atoms. So there are some pairs that differ in terms of the number of hydrogen atoms present. For example, carbonate, CO3 2 minus, and hydrogen carbonate or bicarbonate. So you may be familiar with sodium bicarbonate, which is baking soda. In such pairs, the charge on the ion that contains hydrogen is always one less than that on the other ion. So the charge in terms of magnitude. So for example, CO3 2 minus is carbonate, but by adding the hydrogen, that becomes HCO3 minus, or we could have PO4 3 minus, which is the phosphate ion, and we could also have HP, not shown here, but HPO4 2 minus, which is called monohydrogen phosphate. And I think on our previous list I might have that. So let's see. So this is hydrogen phosphate or monohydrogen phosphate, and then this is dihydrogen phosphate, and then we also have phosphate. So phosphate, hydrogen phosphate, and dihydrogen phosphate. But notice 3 minus, 2 minus, negative 1. So the magnitude of the charge is less. Or another way of thinking it comes closer to 0. So how do we write formulas for polyatomic ions? So in much the same way that we did when we involved these monatomic ions, so calcium and chlorine. So again, we crisscross the charge and we write these charges as subscripts. Now the only thing is that since we have this group of atoms, whatever we do to one, we have to do to the entire group. So that is, if we're placing a subscript other than 1 behind a polyatomic ion, then we have to write it in parentheses. So if we're placing a subscript other than 1 as the final one, so if we're going to reduce it to 1 and 1, or reduce the subscript to 1, then we don't write parentheses. But if 1 is our final subscript, then behind the polyatomic ion, then we have to place it in the entire polyatomic ion in parentheses. So for example, this 2 would go here, and this 1 would go here, but since we're placing a 2 behind this ammonium polyatomic ion, we have to place it in parentheses to indicate that this 2 will be distributed onto all of the atoms in this polyatomic ion. But if we're, let's say here we have equal magnitude 1 and 1, so we know the subscripts are going to be 1, then no need for a polyatomic ion. So we just crisscross, or we know that the ratio of the subscripts will be 1 to 1. Or likewise here, so equal magnitude means we're going to have subscripts of 1 to 1. So like we said, when a cation and anion of unequal charge, combine, use the ionic charges to determine the relative number of each ion that is needed. The polyatomic ion is enclosed in parentheses, and a subscript placed outside the parentheses is used to indicate the number of polyatomic ions needed. So let's look at what happens when magnesium cation and hydroxide polyatomic anion form a compound. So again, we crisscross the charges, but because we're writing the subscript of 2 behind this polyatomic ion, OH, we have to put it in parentheses so that the 2 refers to the entire group of this polyatomic ion. So then how we look at the formula unit of magnesium hydroxide, so everything, like kind of in math, everything outside the parentheses distributes onto everything inside the parentheses. So we have 2 oxygen atoms and 2 hydrogen atoms. Okay, so your turn. Write formulas for the ionic compounds formed from the positive and negative ions shown, and we have 1 or more polyatomic ions involved. And also see if you can name them, and you may need to refer to that list of polyatomic ions. Okay, so again, crisscross, applesauce. So okay, so let's write it. So Na2SO4. Now notice this subscript was originally there behind the oxygen, and so that remains. Then again, we crisscross, so MgNO3 2. And then here we're going to crisscross, but because the magnitude is going to be 1 to 1, then the subscripts are going to be 1 to 1. And notice we don't write any parentheses in this one or this one because we haven't written or introduced a new subscript behind the polyatomic ion. So this subscript was already there as well as this one. So we don't need any polyatomic ion. So the names of ionic compounds containing polyatomic ions are derived in a similar manner to binary ionic compounds. So if the polyatomic ion is positive, its name is substituted for that of the metal. If the polyatomic ion is negative, its name is substituted for that of the non-metal ion. So let's see. Yeah, well, so this one would be called sodium, and then this is the bicarbonate ion, so sodium bicarbonate. And then see if you can name this one, so aluminum sulfate. So aluminum sulfate. Okay, more practice. So pause the video, write the formulas, and name the compounds. Then come back. So we have Ca3, and then PO4, 2. So this is calcium phosphate. So calcium space phosphate. Try to make that clear. There's a space. Calcium phosphate. Then this would be Fe2 SO4 3, and you get a gold star if you remembered that this was one of the transition metals that can have variable ionic charge. So if you said iron 3 sulfate, then you are a great student. So iron 3 sulfate, and then so then this one we crisscross. So this would be ammonium carbonate. Okay, so what is the formula for aluminum carbonate? And I'll help you. So this is the carbonate ion, and so your turn. Pause the video, make sure you know how to solve a problem like this. So aluminum, we have to look at the periodic table for its position. So it's in group 3, so Al3 plus carbonate. So then it's Al2 CO3 3. So the correct answer should be A.